And sure enough, my laptop
And died.
so it's fine. So we have 3 computers on our desk.
Alex is asking a question about that. No, you won't have a grade for each question back through Brightspaces. I don't really have a way to do that simply. However, if you do want to know your personal breakdown on which questions got which, if the explanation I gave today wasn't adequate enough to see where you have lost marks, then please do come to me and we can go over those question by question grades, or marks, I should say. Okay, I do have them recorded. I do have the rubric and metric recorded. Just I don't really have a straightforward place to put that on Brightspaces the way we've got the submissions set up. All right, Alex, fair? You can set up a time with me. I'm hoping that my explanation there was detailed enough to cover off most people's concerns. But yes, office hours would be great. If office hours don't work for you and you would like to find another time, please do reach out to me. However, take in consideration that my time and your time, okay? So Mondays are best. If it doesn't work for you, I'm more than happy to try to find a time that accommodates both of us. All right, thank you, Georgia. Okay, let's dive into it. That wasn't too bad on timing. We almost hit 20 minutes, which is good. Okay, so what I want everybody to do is pull up their notebooks from last week. If you're comfortable starting a new notebook and pulling across where you got to last week, please do if you want to take different notes. Otherwise, pull up the notebook you had from last week. And what I'd like everybody to do is take 3 minutes, 5 minutes to bring in your libraries, bring in your data. And where did we get to? We got to parsing the data into our single variable parameter and grouping by the max for each given year. And we made sure that we had that put back into a data frame. Okay, so the full code is right there on the screen if you were missing something from last week. But please, everybody, get up into Jupyter, get that up there, get your data loaded, and take a look at what your variable looks like. All right, and then we'll move on from there. We've got a few things to cover. Okay, how's everybody making out? Who can tell me a little bit about what we've done here? So what was the data? Where did we get it from? Why did we do what we've done? And what our resulting table represents? Surely somebody kept notes from last week. Ah, Rachel, thank you.
Basically, we had data that was divided using a parameter of either 1 or 2. I don't remember what that was for.
Good thing to make notes on. Goes for everybody.
It's flow
But
or
anyway,
stage.
Nigel, thank you. Yes. So sorry, Rachel, that Nigel spoke up there. He said flow and stage. Great. Thank you.
Okay.
Continue, Rachel. You're doing great.
So anyway, so we then had to go through and subset it to this like DF1 subset, so that we only are looking at the flow parameter. And then when we plotted that, we got a box plot that was slightly more representative, but maybe still has an outlier or a few.
Good. Yeah, great. Okay, thank you. That was great. Where did we go from there? So we got our subset, our first subset by looking at, we have the value with parameter 1, which we've determined is flow or discharge. Who recalls what units were? These are things you should be making notes of or putting in your notebooks. Nigel, yes?
I believe it was meters cubed per second.
Correct. How, Nigel, do we find that?
It's in the data if you look at it
Great.
separately.
So, perfect. Thank you. So any of you who didn't know that answer or didn't have these answers on hand, please make sure you add them to your notes or your notebooks here. So we've all learned how we can either add a cell that's a markdown cell if we just want to type some things in here. We've known that we can put a hashtag in front, that the code that Python ignores, that you can put notes in. Please leverage note making. These are things that we went over last week about the parameter 1 and 2, what they mean, why we took one over the other, and where that information came from. So make some notes if you didn't know those answers that Nigel and Rachel provided for us. Okay, so somebody else, Rachel's got us to the point where we've got a subset using value and parameter 1, and she's quite rightly said that we took a look at a box plot there. It looks like there's an outlier. Great, just gives us a little bit of information to go on from there. There's 2 other things I've done on the screen here that we all did last week. What are they and why did we do them? Nobody knows why we did the second line in the last cell that's up on the screen, df1.groupby df.index.year.max.
Wasn't that to just look at the maximums of each year? So that we
Correct.
just look at the extremes?
Excellent, right? We're looking at working with flow data. We're looking at events, extreme events. And we're looking at trying to find, 1 in 10 year, 1 in 50 year, 1 in 100 year type events based on our data set. So we don't need all the data points that are in between. We're looking for these extremes or these maximum annual flow amounts, records, data. Great, thank you, good. So that's what we're doing. What is the result? Let's talk programmatically. What is that on the screen? So we know we're only wanting the maximum flow for a given year. Somebody give us the quick breakdown of how we're going to do that and what it results in programmatically. Okay, so last week I gave you the Pandas documents page that we've been using throughout the term. And I'm fairly sure I gave you the one directly, otherwise you could have looked it up, that does group by. Tells you what group by does. We've already seen the .index.year. We've already used max in another form. So these should be somewhat familiar to us. We know that if we do .index.year, we're looking at our index. We know what our index is because we set it up here. It's a date time index. And so we know we can pull the year from that. So this bit here is telling we want the year of our data index. And the group by is telling us we want to group by the year. Then outside of that, we've got our max. So we're only looking for the max value of a given year that we're grouping by from our data frame. We can read it straight back. Then somebody tell me what this is. So if I just took this, okay, that's the result. Okay, so we know what this is, right? Because we just talked about it. How do we use that? Why if this worked? What have I got? Sorry, I'm trying to hide the one below. Why am I using this? What is this? Everybody should know this answer by now. Please speak up.
That's just like a subset to
Yeah.
use just the max values.
Right, but what type of format is in? What have we been working with? What's our primary format, data format? This is important. We did talk about it last week, and I would expect you've got some notes or some recollection. So it's even on the screen here. Does this, so what's happening here is I'm looking at this group by that we've just discussed. This is what it looks like. What data format have we been working with almost exclusively for this term thus far? What's it called?
Is it a string?
It's a data frame, right? So every time we've been doing anything, we've been looking at a data frame. So anytime we do our read CSV, that's why we've been using the DF shorthand, okay? So our data frames up until now and everything we've been doing look something like this. They have an index that gets put as bold on the left-hand side. There's a header with a line of some form. We've got our column names at the top. This is our expectation. This is what it looks like. It looks like a table. It looks like Excel. That's what we're used to. That's our norm. That's kind of what tells us we're in a data frame because we started there, and you know we haven't been diving into a lot of data types. This is our home. We want to stay here. Does this output in our group by look like a data frame?
No.
No. Thanks, Nigel. Okay, so now we know that here, our df1 max isn't in a data frame. Okay, all we would have to do is look at it. I implore you, every time we write anything or we assign a new variable, that you look at what the new variable is. We've talked about this. Every time you load in using the read CSV, you get a variable and you want to look at your data. The reasons we've done that in the past when we do our read CSV are things like spaces in our column names. We're using comma separated data. There's a whole slew of things that we've gone over there. The same applies when we're manipulating any of the data through the steps in our labs. We should know and understand what the object, what the variable, here in this case, I've named it df1_max, what it is. In this case, we may not know what it is because of our experience level, but we know that it doesn't look like a data frame. So if I were to, let's see here, let's get rid of this cell. And let's add a few here. And so if I was to do our box plot, I believe, box plot, and help me out if I mess this up. You have to have something in here, right? Column name. What do we have to have inside our box plot? Do I have to look up?
Oh, you want the value?
The value. Oh, the column name value, right? So it just has to say something like
The
that.
string.
Yeah, and,
Yeah.
and
Okay.
does it have to be in square brackets?
No. Okay. That would help. Okay. Does this work? No. Okay. It should start becoming more and more obvious here that it is not a data frame. It's using a word that we're maybe not familiar with. The object has no attribute, box plot. What does that mean? Now, box plot worked before we did this group by. It's telling us that it's something called a series now. What's all this about? Okay. So by looking at it, we knew it looks different than a data frame. By trying to do our box plot again, which is what we did last week, we run into an error that we're not familiar with, that it's something is called a series. But why? It should be a data frame. Aren't we working with data frames? Okay. The result of our group by puts it into a series. So the third line I've got here is I'm putting it back into a data frame. The data frame is our home. It's what we're familiar with. It's where we'd like to stay, because it will stop things from like this from happening on some of the queries that we've been used to. Okay, so if I do that now, if I put it in using pandas, PD, our alias, data frame, capital D, capital F, and then just put our df1 max, our variable, inside our brackets there. Okay, this is our series, but we don't need to go into details of what a series is. We're just going to go back to our data frame. Okay, and now my box plot is generated. All right, so that's a recap of what we did last week. Any questions on that, other than everybody should be scribbling down notes, since it was dead air for some of that? Okay, load your libraries. I'm not too picky about this, as long as you've got pandas in there. We'll be using NumPy later and our plotlies. So this is familiar. You can have more. If you have less, you'll have to add it. Just make sure you've got enough. If you run into a code error, you can always have more in here. You want to put everything in there, that's fine. Got your load libraries in there that you think you're going to use at this time. You can always add more later. We pull our data in. Okay. I want to ask one more thing about our data here. Did we run into any issues with a particular No, I'm not going to go over it. I'm just going to tell you. So we had to make sure that we parse dates and that we set the index by date. We had to be really careful about what our date was, because we had a date column that looked like a date, but Python didn't recognize it as a date time, which is why we had to parse dates. So please, in your version, if you do not have the parse dates in there, please throw it in there. You will need it for our index.year to work. Otherwise, our index is not in a date time format where pandas or Python recognizes it as being a year. Okay, got our data in. We made a couple of additions here. We set the index. We sorted the index. And then, as Rachel helped us out with, we did a mask on our data that gave us a subset where we're only dealing with the param, with the records where the param column equaled a 1. Then we took that data set that we just created, the subset, then we did a group by year, looking at the max value. We put that back into a data frame, and now we are left with our familiar looking data frame, bold header, column name format to work with. Okay, there's our catch up. Any questions?
Do we have to now do the same thing for our stage parameter?
No, we won't be using it. I'd let David talk about it more, but I wouldn't worry about it at this time. We're just not going to be using it for our analysis. The data is not quite complete as it would be, and just for now, let's leave that behind, and we're just going to use the discharge, the flow data for our analysis. Okay, good question. Thank you, Nigel. That's great. It's a good assumption. Do we parse it out? Okay, so moving on from there, I am going to send you a web link over the chat, and this you can follow that link, but I've also included the relevant piece, as it were, on the screen here. There's a lot going on. I might add a few different cells here to break things up so that we can look at it one by one. So bear with me here. Okay, so if you follow that link, that gets to a web page. I would bookmark that, and I would take that link and I'd put it right in to your Python notebook, your Jupyter notebook, as I did here. You could throw it in a markdown cell if you'd like, or just comment it out, make a note of it. It's a good reading. We don't need to read over it right now, but I would make sure that you do read over it to help you understand some of the things that we're going to be looking at. Forgive me, I may change gears because I have skipped something. This is where we'd like to go first. That's what happens when you got more than one notebook going here. Okay. So excellent. All right. So David, if you're still there, I'm not gonna ask the students, so don't try to copy all this down. I'm gonna just put this into my notebook that you get, but I want David, I could do it too, but David, I know you've got some good comments on this to talk about what we've done here. So David, this is the graphic where we've got the QQ plot that we're making, and I'm pulling in the sub data set, and this gives you the 3 image graphic as it transforms, right? So the first one being just the QQ, the second one has got the gamma, the third one is taking away our outlier.
Right. So a QQ plot is a way to check that your data match a certain fit, so a certain type of curve. The curve that you've seen most often is the Gaussian distribution, so the bell-shaped curve. Not everything in nature follows that sort of distribution, and we're getting into a territory where that's definitely the case. So with something like the river flow data, if we were to plot that in sort of like a histogram that we've seen with the Gaussian distribution, it doesn't follow that bell shape. Instead, we get a lot of values clustering near the low end, and then we have a number of values sort of that spread out towards higher ranges. This is called a long tail distribution, and part of the reason that it forms a long tail is it has what's called a hard left edge, meaning 0. So we have precip or flow data. The lowest that the values that these can take, of course, are 0. So there is no, negative flow type of thing. And so if we're going to build a statistical model, so this is another variation of a statistical model. We're fitting a parameter, we're fitting a parametric equation, which is an equation that is defined by parameters. Again, in the terms of Gaussian, the parameters are mean and standard deviation. Those will give you the shape of the curve. The process is the same, but the curve is different. And so we want to fit a curve. Why? Because we want to draw inferences. And so we're coming around to the idea of what is the 1 in 100-year return? What is the 1 in 500-year return? In the particular case of this example, we've got one extreme value, this very extreme 2013 event. So it's of interest to know, is this event the 1 in 100-year event? How does this event compare to what we would have predicted using all the other data to be the 1 in 100-year event? Does it exceed that? Is it under that? How does it compare to that? So we can use a QQ plot to say, well, are the data actually matching a Gaussian distribution? Is it reasonable to assume that? Or do we have to find some other distribution like a gamma distribution? There are tons of these distributions, by the way, of these parametric equations. You'll see in the paper that we give you that Pomeroy et al. Use a Pearson type 3 distribution to fit the water data. So the idea is, if your data, QQ stands for quantile. So we basically take the quantiles of a theoretical distribution. You can see on the x-axis there. If we had a perfect gamma distribution in this case, the theoretical quantiles would line up that way. And then if we plotted a set of data that had a perfect gamma distribution, the QQ plot all those little dots would line up along sort of the y equals x-axis. They would all be perfectly lined up.
Oh, sorry, David, I don't mean to interrupt, but I think you're saying on the first one here, this is theoretical quantiles for a normal distribution.
For a normal?
Yeah.
Oh, okay. And
and that's why, and that's why it's not laying out straight.
Okay, right.
And then the bottom one is gamma, which is why the quantiles have a hard 0.
And why they're lining up better.
Yeah.
Oh, okay. Thank you very much. Yeah. So actually, that's a perfect example then. So the second plot, the theoretical quantiles are drawn from the gamma, or from a Gaussian, sorry. And in fact, you can see very much that our data just don't match that, because, the first part, they're above it, second part, the middle part, they're below it, and then they kind of come back up again. And that's an indicator that, okay, we cannot assume that these data are Gaussian. So we need to find another distribution that better matches the form of the data. And then the next plot shows Gaussian is a lot better. We've
Gamma.
got that straight line, or gamma, sorry.
Top one Gaussian, second, bottom one gamma.
Thank you. Yeah, so the gamma distribution, or basically some long tail distribution, is where we have to go with these data. Otherwise, the inferences that we draw are not going to be accurate. Anyhow, that's all that's about. So just, we were initially thinking, oh, we should take the lab in this direction, but it's just kind of getting too much. So this is just a demo of that concept. So if you ever encounter a QQ plot, this is what they're trying to do.
And then this third one in the list here, David, is when we take out that extreme value.
Right, yeah. And so that's actually an interesting indicator that, this is very distinctly a situation where we have an outlier. It's an outlier we want to capture because it's a hard indication that the watershed can behave in this way. But, it kind of presents us with a bit of a problem, because the data fit without that point. The data up until then had fit the Gaussian or the gamma distribution very nicely. And so the gamma would be perfect for making predictions. But then bang, we get this one strange event. So part of the issue is to try to figure out, and this is will be part of the lab exploration in association with this paper by John Pomeroy and al. And company in 2013. They review some of the reasons for this event. So part of the exploration is well, why might this event have been an outlier? Why did it exceed, expected return frequencies? Yeah. Thanks, Adam.
You are. Rachel's just asking QQ plots again.
Right. Sure. So if
So
quantile.
And I'm also going to provide a link while David does that.
Okay. Yeah. So remember what a quantile is. So like the median, which is the middle observation in a data set, we have these what are called measures of central tendency for a data set. The mean or the average is the most typical one people think about. And that kind of gives you, that's a measure of central tendency in a data set. And that kind of gives you like, what's the most commonly occurring value. Another very typical one to use is the median, and the median is simply the middle value. If you have 11 observations, then the median will be observation number 6 in a ranked set of data. It's also called the 50th percentile or the 50th quantile. So a quantile is the percentage, how far into the data set you are, in a sense. So the 5th percent quantile is like 5% into a data set. 50th percent is halfway into the data set. 95th percentile, you're 95% of the way through the data set. And then, you can sort of fill in the gaps with all the other quantiles in between. And so you can map a theoretical distribution, like a perfect Gaussian or gamma curve, or well, any curve, perfect, even a uniform curve, like rolling at one 6-sided die, that's a uniform distribution. You can map any of these distributions, a perfect version of it, onto theoretical quantiles, and then you take your data set and map the data set onto the same type of curve. So you map your data set onto a gamma curve. And then if they correspond, they're going to line up in a straight line. So that's what's going on with these QQ plots. Does that make sense? A little bit?
Yeah, thank you.
And I'm not going to dwell on it, but this is the code. And as I said, I'll provide it to you so you can run it and reference those plots just as we've discussed. But I'm not going to go into what it's doing. It's using SciPy stats, which we touched on before, but I'm not going to go into it. And I will also provide you with this bit of code. You're a little more familiar with the format of it since it's using plotly instead of matplotlib, which is the set above, which just gives you the added hover text ability in a format you're familiar with. But as you can see, it's the same plot without its axes labels as this one here. Okay, so that was just a plotly example of the same data set. Okay, all right. Thank you, David. That's great. We are going to move on from those, and we will provide those two snippets of code with the full notebook. Okay, and for demoing today, I'm going to remove those. All right, so where we left off before, I sent you a web page before the most recent one I sent there, Quantiles one, and then before that I sent you another one there that talks about return intervals, which is where we're going to go next. So pulled directly from that site is this snippet here. It says for each data point, a recurrence interval is calculated using a Weibull equation. Ri, recurrence interval, equals n plus 1 divided by m. The peak discharges are ranked from m equals 1 being the largest, and 2 the second, and so on to m equals n. So n here is the count of your data set. So how many records in this case would be years, because we've taken a single max value for each of the years in our data set. So now we've got those three, we've got this equation, we're going to recreate it in Python and populate a column that tells us our return interval. So the first thing we need to do is rank our data. Sorry, I keep double clicking that. The first thing we need to do is rank our data. Okay, now I'm going to jump up here again. I apologize for jumping around, but I like you to have the web pages for your notes and up on the screen if you have space. This one here, that I just sent over the chat gets us back to our Pandas documentation, which you should be familiar with the layout now and what it means. For our data frames, knowing that we've still got our data inside a data frame, there is a rank function that we can employ. I'm not going to go over all the details in here, but you can read it at your leisure. As before, there's some examples at the bottom that can be easier or not so easy to navigate depending on the function. But this is the function we're using. This is the documentation on it. So using what we've known there, and I apologize, I do want to not move around so much for you. There we go. Okay, so here. Okay, what are we doing? So we know from past, if we want to create a new column in our data frame, we can do that by stating our data frame name, and then inside square brackets, we can put some string, and that's just going to be the name of our column. So this is a net new column. This is anything we want it to be. So I've named mine ranked, and this is just my note to know that I've got a column that ranks the data in there. So data frame, column name, new column name that you're going to create, and then we've got an equal sign. So what are we going to put into this column? We are going to use our Pandas rank function. And if you were to read up on that documentation page, you'd see that we need to define what we want to rank prior to the rank function. So in our case, we have our value column that we know is our flow or river discharge. And we've used the same formatting, which is our table, data frame name, square brackets, and the column name inside. I will make a note that Python is case sensitive, as we've discovered, and it's a capital V in the value column that we brought into our data frame. From there, we're going to use our rank function. All of our functions have an open close bracket, highlighted green when you click on it. Inside those open close brackets, I've got two arguments. For our purposes here, I've specified ascending false. So the default ordering of rank or ranking of the rank function is ascending, which means it will go ranked 1 to n from lowest to highest. But we know from our little article up above here that we want it to go from largest to smallest. So we want to set the argument ascending to false, which means we are now ranking in a descending fashion from largest to smallest. The second argument I have in here is named method. I won't go into all of the options for method. It is in the documentation if you'd like to read it. We don't necessarily need this because we don't have the likelihood of us having duplicates in our list is low. However, if we had 2 years where the maximum flow was identical, we can specify the method by which we want to order those identical values. And since we're not really concerned about how we do that, I've used the method first, which means it just takes the first one of the two. Because we're not really concerned about the year ordering. We just need a rank system of our value or our flow records. Okay, similar format to what we've seen, net new column, using our values, ranking them in a ascending equals false, so descending, and our method of selection in the event there are duplicates will be the first record that it comes into the function meets. Okay, make sense? All right. So now that we've got our m value as part of our ri n plus 1 divided by m formula, what term are we missing now? We're missing the n. So I've mentioned this before. What's n? Anyone?
The total number of data points or like values we have.
Right. So it's a record count. How are we going to get n? Anybody got any ideas? We may have used a method to get this once before. But any thoughts? Anybody seen the code before? Any idea how we could get the number of records?
Is there like a count function?
It's a good one. You could try. There is a count function. It's not going to work for us, but good. Good idea. We're actually going to use a bit of a shortcut. Okay, there's a really simple, straightforward function called len, which is short for length. And all this does is it calculates the length of whatever you put inside it. So in this case, I've just called my data frame. I want to know the length, the number of rows in my data frame. So I will say that this is a shortcut, right? This isn't specifically counting the number of rows with some value in a column in a data frame. We could go to that level, but we don't need to. We just need a quick shorthand to figure out how many records we have in our data frame. Okay, so if you do length, data frame, it just gives us a straight old integer, straight number. That's all we want, right? Trying to keep it simple. We just want a number as our n. Okay, so now we've got our m for each of our records, each of our values, and we've got our n. So now it would be nice to have our return interval, our ri. Okay, so to do that, we are going to write our formula. So those of you who may have dabbled in how to do this in Excel, many of us have, it's very similar in Python. So let's walk through it here. So just like we created our ranked column in our data frame, I'm going to create an RI column. Same format, same method. I'm going to go data frame, df sub, open close square brackets, and a string inside of there that I want my column named. I've chosen RI. You can choose whatever makes sense to you and you can keep track of. But RI for return interval is part of our equation. Next, I have quite literally copied the equation from the article up here and pasted it down into my Python window for my column calculation. The n plus 1 is pretty straightforward. We can just leave it as is, right? As long as we create n. We know n is 56, so we could either go n equals, we know that now n is going to equal 56 because we just tested it. Okay, so now we've got n. Or we could even just put 56 in there if we wanted. I'm going to keep it as n because we've just explored that len data frame is 56, and I can just make that n. So now I know n equals 56, which is our count or length of our data frame. And so I've copy and pasted my n plus 1 inside brackets, open close brackets. From there, we've got to divide by, and that's just the forward slash. Same as it is in Excel, same in Python. Our forward slash means divide by. Next, we want our m. Right? We're dividing by m. So we worked on that up here. We created a column named ranked to create our m value, being our ranked value for our ranked value for our discharge values using the rank formula. So I can just call that column. Got my data frame. I'm going to use the ranked column, and I'm going to put this formula in to create my turn interval record for each row in my table. So if we get through these three, we execute these three. Now let's take a look at our data frame and see what it looks like. So now we've kind of expanded our data frame a little bit from just having our value to now having a column that tells us the rank, excuse me, from 1 being the highest value to n being the lowest value. In this case, we've explored that that's 56. And then we've calculated a third column here, giving us our return interval. All right. So I would like a volunteer to give us a go at explaining what this return interval is. So that web page I gave you that had the formula we just worked through here, the return interval, this little snippet I pulled from that web page I sent, explains what the output of this column, the return interval, means. So volunteer to see if you could tackle explaining what 14.25 or 67 means, a return interval 14.25. Alex, have you turned your mic off because you were volunteering?
Yeah, sure. Is
Awesome.
it like the likelihood that an event of that magnitude will happen like every 14 years? Or
Yeah. The article talks about it a little more specifically to what the RI in this case means. You are absolutely correct that we can interpret it that way for our uses, but I want to make sure we're just a little careful to understand what the numeric number means. So what we've actually calculated is, and it is in that article,
sure.
but you are absolutely correct that that is how we can interpret the value. So what does the raw number mean in the data world?
The average time interval between the occurrence of 2 discharge events?
No.
Oh, okay, never mind.
We're right. Alex has got it totally right that it is, we can say that, the return interval, the chances of it happening is, 14-year type, or 1 in 14-year type thing. But if you read through that article, the value, in fact, gives us a probability. So we can say that there's a 1 over 14.25 probability of a discharge value of 1230 occurring in any given year. So that's 1/14 of a probability in any given year that a discharge value of 1230 will occur. So that's it numerically. But hearing me say that, do you kind of see how what Alex was saying about the 14 years makes sense? how you can kind of make that leap from the explanation there to that kind of 1 in 14 year type, I don't know, the way you say it, as it were. Does the Edge is asking, is the sum of all RIs equal in 1? No, not at all. They're independent. The RIs are directly independent of each other. I mean, technically, because it's based off of a ranked data set, they aren't. But anyway, I wouldn't go down that path. The way to read it, like it outlines in the article, is, for example, like let's work on one of the smaller ones. So let's say that this RI, if we round it, equals 1. So this is a discharge value of 136 cubic meters. We gave that a rank of 55 in our data set. Okay, understand that the rank is only applicable to our data set. And the return interval was 1. So knowing what I just said about the one above, what can we say about this 136 discharge value?
That's a discharge value that we expect to get any year. Like it'd be like an average, or like maybe not average, but common
Right.
Achieved.
Exactly. The likelihood that this station, river station, will experience a discharge value of 136 meters cubed is 1 in 1 on any given year. So that's 1 over 1, that's 1 once, which is 1. So you pretty much have 100% probability of this river experiencing a discharge value of 136 in any given year. Okay, so then we can move up there to see some of our more extreme values, like we were talking about this 1230, 1,230 cubic meters discharge, and we use the same thought process. The probability of that occurring is 1 over 14, 1/14 for any given year. Okay, so I hope that follows. That's what that website that I sent and linked you to explains. Right, 1/14 probability of the 1230 discharge value occurring on any given year. So if you want, my math is not good enough to do what that is. So a 7% probability of that value occurring. Okay, it's just in fractions instead of in decimals, but it's still probability. Okay, all right. It's important you understand that. Julia is asking, the higher the RI, return interval, the more extreme or likely the discharge rate will happen in any year or a specific year. Not a specific year, but in any given year. So it doesn't matter. Good, Nigel, thank you. So if this year there's a 7% probability that 1230 discharge is going to happen, next year there's the same probability. It's a 7% probability of it happening next year. The year after that, it's a 7% probability. The probability is not cumulative over the number of years between events. Okay, and yes, the higher the RI, the lower the probability gets. So if I make this 16, the 7% is going to go down to 6% probability that it's going to occur. If I decrease the RI value to say 7, the probability becomes 14% likelihood that that discharge value will occur on any given year. All right. Yeah.
Wouldn't the probability change every year that is added to the range of years? Like say there was like, so after in another 10 years, there'll be 66 points in the range. Wouldn't that change the
Correct.
probability?
So you have to be careful here. You're absolutely correct. If you redo your analysis in 10 years, then you're adding 10 years worth more of data, your rank changes, and you're recalculating your return interval. But with this data set, you've calculated your return interval. So you only have that to predict out. So the probability of next year, 2 years, 5 years, 10 years doesn't change year to year until you rerun your analysis, right? You're absolutely correct.
Even if that rank stayed the same, like say nothing in the top 4 ranks changed, so we're still looking at the 4th ranked, like the 1200 one.
Yeah.
That probability would stay the same or no?
If you add values to your data set, it'll change.
Okay.
Right, and we're gonna put this onto a graph too, that hopefully helps a little bit too. And we're gonna do that now because we're running out of time. Okay, so make sure you understand that component. You've got that web page, read through it, get your head wrapped around it. It's important that you understand what the data we've generated means. Because if you don't, interpreting it is going to be much more difficult. If you need additional resources, you can go hunting around for them. This isn't unique to this page. Although caution not to get too far afield that you start making things a little foggier for yourself. All right, so we've got the new data. We've talked about what it means. We've got our return interval. Great, wonderful. Let's move forward from that. I don't expect you to copy this down. I will provide it, but I want you to pay attention to it so you understand it once you do get it. And I'm not going to go over the math in too much detail. What I want to do is go over the plot in more detail. But at a high level, last week, we didn't use this last week. We haven't used this yet. This was did we use? Yes, we did, right? We used this for, yeah, we did. Okay, so this is just a little snapshot back in time. This is lab 3. So we used our linear regression. We set an X and Y. We made our, well, it's not there. We made our plot, right? So we did some array model prediction, linear regression fit, right? Blah, blah, blah. We did that. This is very similar. I'm pulling from a different library, but I'm doing the same type of method. So I'm going to set an X and a Y variable. I'm going to use my data frame value, my discharge, and I'm going to use our newly created data frame return interval. Those are my 2 X and Y for my analysis. I'm going to then run a linear regression against the X and Y. Don't worry about the other stuff right now, just high level linear regression against my X and Y that I've created above. Then this linear regression gives me an intercept and a slope. And I'm going to add my intercept to my slope, multiply it by my X, and then I'm going to plot that. So I'll change this code around a little bit to make it a little more familiar to what we've seen in other labs, but it's doing the same thing. We've got our go figure. This is our plotly, and we're going to put one scatter plot on our plot, and these are going to be markers. These are going to be the points. And we're going to have an X and a Y. Our X is going to be our data frame return interval. Our Y is going to be our value, our river discharge. We're going to add a second plot to our plot. In this case, we're going to add a line. So we've seen this before. We're going to use our our plotly scatter, we're going to call it a line. And for this x, we're going to use our return interval, the same as we did for our markers, for our points, record data points. And we're going to set the y to this res y variable that I've named above, which was created by the linear regression intercept plus the linear regression slope multiplied by our x, which is our return interval. Then we're going to add a little bit of tricky stuff into here. We're going to actually change our x-axis on our plot to be a log axis. Okay, not going to go into details there. If we have time, David can maybe talk to it, but it means the x-axis looks like this. So you'll notice that the little boxes on our plot have different sizes. So it's important to understand that part, that this is not the distance between these is not equal. It's actually in a log form, okay? Similar to the QQ plot in that term, but it's in a log form. So when it says 10, it's actually 100, okay? And no, I lied, sorry. 10 is 10, 100 is 100. The 2 here is 12, because it's 10, 12, 13, 14, 15. No, geez, 50. It's to the 10. Log isn't something I work with very often. Forgive me. Okay. Once we get to 10, then we're going up by a larger increment, right? So this becomes 10 to 20 to 30 to 40 to 50 to 60 to 70 to 80 to 90 to 100. And it goes on from there. So it's like a base 10, right? It's log. David, maybe you can help me out there. But on the plot, we've got our data points in blue here that are our values, that are our wildcard way up here. And we've got our linear regression line straight through there. So we saw this on the QQ plot, looks very similar. We see that the line kind of pulls up a little bit from what we've got as if we were to just take a pencil and draw a straight line, because it's floating way up here outside of the norm. Okay, so we are gonna want to take a look at what that looks like without that extreme value, right? This outlier, because we discussed that in the QQ. So I'm going to add that in here. Again, you're not running the plot yet, so don't worry about this, but I'm going to remove any values above 3000, which is this value floating up here at 3320. I'm going to rerun my plot. And now it's looking much, much cleaner, like our QQs did, right? So as long as we can rationalize taking out that extreme outlier, our statistical plot here is looking much better for us to be able to make predictions on. Okay, looks really quite good, doesn't it? So now we could use this regression line to make some predictions out from here. All right, so for example, and since we've got our nice plotly charts, if we, oops, don't do that, 0. If we wanted to figure out where our 3000 should have been, right? If we didn't include that in the data set, it hadn't happened yet, when would we have thought it would happen? Well, similar to what we did last week, we could eyeball it. So it was about, I'm gonna squish it down again. It was about, 3,300. So somewhere up here on our y-axis. So if we want to come across at the top here, we want to just imagine we had a pencil, draw the pencil line up to somewhere up here. That might have been something like a 1 in 500 maybe we draw it up here, somewhere around here, maybe. It'd be a 1 in 500 year event. Okay, what did we have it at before? A 1 in, I don't know, it was up here somewhere, wasn't it? A 1 in 50 year event. So there's lots of reasons to explain that, a lot of reasons to explain how crazy that event was. If we hadn't had that event occur and we had all of our data and we predicted it was around 1 in 500 year, we would have said the probability is about 1 in 500 in any given year, but it occurred, which means that that's a pretty significant extreme event to occur. 1 in 500 year event. Pretty crazy, right? That's how this all kind of works. Now, last week we did figure out, well, we don't need to eyeball it. We have a formula. Guess what? We've got one here too. I'm going to hide my screen for half a second because I don't want to give you the lab questions. Okay. Thank you everyone for bearing with me. I know we've got about 10 or 15 minutes left, but let's keep up this pace. So the formula that we used in our plot, where we used the linear regression stats function, and then we used a intercept and a slope plus our x, or log of our x, because that's how we were plotting it, our x, to get our y values, which was the line, right? So this is the line on the plot. So if I want to use that same line, I can manipulate it, right? Reorder, rearrange my formula to get me some answers. So once I've run my plot and I've run my linear regression, I can now say, okay, so my linear regression intercept plus my linear regression slope multiplied by the log of x. What's x? Anybody remember? This is important. What's x?
Is it return interval?
Correct. Okay. So we learned what return event in the numeric value of return interval was, but what did Alex tell us it was conceptually?
A probability?
That's what I said it was in the raw numbers. But what did he say the return interval was conceptually, and what we are using as terminology on the plot? Come on, Alex, you remember?
The likelihood of an event occurring to that same magnitude, like in years, I guess.
Yes, perfect. In years, right? So if we've drawn that parallel, we know what the real data is and how to use the RI, and we've plotted it and we've seen it. So if we wanted a 1 in 100 year return, we could put 100 in here, replace our x with 100 for our linear regression line, and it will give us the, let's even change the verbiage here so it makes more sense. Let's see, it's the flow or river discharge value, okay? Because that's what it is, right? What is the river discharge value using our linear regression for a 1 in 100 year event? I'll take this out. Okay, gives us 1964 or 1965. So the 1 in 100 year expected or predicted, I should say, let me use my words better here, the predicted river discharge value using our data set and our calculations for a 1 in 100 year event is 1,965 cubic meters. Is everybody following that? This is doing the same thing as extending that line. Okay. So now, what did we really want to use it for? We wanted to see what the expected probability, 1 in how many year, for our lingo here, 1 in how many years for a given discharge. Also gives us a way to verify our formula, right? This is a generalization. This is our linear regression. So it's not direct data points, but it is a regression built trend or statistic best fit built on our data set, but it is not drawing a value from our data set. So let's instead say for a given river discharge value, what is the 1 in year return? Break that out. I know it's probably hard to see on the screen share, but you get the idea. Okay, so what is my 1 in a given year return if I want to use a river discharge value of 2100? Looks like it's a 141 year. 1 in 141 years is the likelihood of a 2100 meters cube discharge occurring on any given year. Everyone see how that works, how we got from our data set, creating our return interval, understanding what our return interval is, using our return interval for a linear regression, plotting our linear regression, then using our linear regression formula to make predictions on year and on discharge values for a given prediction level, 1 in 100 years, or the 1 in year return for a given discharge value. You see how powerful this can be once you go from looking that we just pulled a CSV file of river discharge values off of the internet. And here we have our own little script, which I'll clean up for you and give to you. Our own little script here to answer anybody's question on, hey, what's the chances that we're going to get an event greater than 2,000 cubic meters? Well, I don't know. Let's try it out. If I just change my numbers up and put it into 2,000, you can say that there's a 1 in 40 year probability on any given year. Okay. We got 5 minutes left. I want to use every minute of it. I want people to ask questions about the understanding of this. I want to make it very clear that we are limited to our data, but not in a bad way. We have a fixed data set. We've used that fixed data set to generate a linear regression that we can now make educated predictions on. we can draw conclusions from those predictions. And we can justify our predictions by reviewing our steps. And that's what I've done here today. We've gone from importing our data to calculating column values, to plotting, interpreting a plot, to then using a formula, in this case our linear regression formula, to return values of meaning. Okay? Let's pull one individual value to help validate our little formula there. So let's use our 1230 again. Okay. So we were playing with that 1230. And what was the year 1 in what that we expected? What am I expecting this number to be if I put 1230 into here? Come on, guys, I'm sure you've been paying attention.
If it's the RI, then it's 14, right?
Right, it's 14. So we would expect, if I run this to be 14 or close to 14. There it is, 15.46. I'd say that's pretty close. Why isn't it exactly 14?
Because we took the value, the outlier value out.
That's a good point.
Wouldn't that change it?
Yes, it would. Which is now getting me second guessing myself on when we take that out. You're absolutely correct. I'm going to make a change to my script here. Good answer. Thank you very much. Great. What I was looking for was that this is the model. Okay, so this isn't our exact data points. So just like you see the red line that overlays our data points, that 15 is being pulled from this line. Okay, so even though our data point in here, where is it, 1230, is very close to the line, it's not sitting on the line. If it was sitting right on the line, then instead of returning 15, we would return 14. Okay? Does that make sense? That it's 14.25 for 1230, but the line is close, but not right on. Now, the reason, so instead it's here-ish, right? It's not doing my pop-up, but you know, if we know that this is 1230, if we come across until we hit the line, it's at 15 point something. Okay? So that's why the value won't be exactly the same, and the closer to the line, the closer the value in our little model will be when we go to verify. And is that Alex or Nigel? Somebody pointed out that yes, I should probably re-rank to make our regression more applicable or precise. So I will correct that. The method is all the same. Everything's correct. But when we remove the outlier, we should be doing the recalculation on our eyes. Okay, we've hit time. Generally, we go over 10 minutes, but if anybody's got classes and other obligations, you're free to go. I would like anybody to ask questions now if they are still not 100% on what we've covered. Well, thank you, everybody. Everybody's 100%. That makes me feel good.
All right, I'll stop recording.